Hydrogen peroxide decomposes to form water and oxygen. The rate of this reaction can be found by measuring the volume of oxygen formed after different time intervals. Hydrogen peroxide solution is placed in a conical flask and the apparatus is set up as shown in figure 3. So you can see there's warm water in here to heat the solution so it's at an optimal temperature for the reaction to occur. And then you've got a conical flask in which the reaction is occurring. Presumably a gas is going to be produced here, and this is called a gas syringe. It's an important piece of equipment which we don't often use in school, but you should be aware of because it's the most accurate method of collecting a gas. And what happens is, as gas is produced, this plunger will automatically start to move backwards as it's pushed by the gas, and you can measure for example, every minute or every 10 seconds what volume of gas is produced because there's markings over here. So instantly state the name of the piece of apparatus labelled Z. Well, we now know it's called a gas syringe. At the end of the reaction, the bung is removed from the conical flask. A glowing splint is put into the gas in the flask. State what you would see. So there's a few ways we can work this out. Firstly, if you look at the question, it says the rate of reaction can be found by measuring the volume of oxygen formed at different time intervals. So we know oxygen is the gas being produced. But if you're familiar with your chemical tests or tests we use to identify various gases, you'll know the glowing splint is used to detect oxygen. So when you put a glowing splint in oxygen, it relights. And this is what you would see. A glowing splint relights. A solid catalyst can be used for this reaction. The experiment is repeated under identical conditions but with the catalyst added. A catalyst is something which speeds up the rate of a chemical reaction without getting used up in the process. An example of a catalyst is an enzyme, but enzymes are found in living things. In industrial processes we don't always use enzymes, we can use other chemicals as catalysts. In the experiment with the catalyst added, which of these is true? The rate of reaction is the same as when no catalyst is present. No, because the rate of reaction goes up. Catalysts speed up rates of reaction. Come back to this one. Some of the catalyst is used up. No, because the catalyst never gets used up. As you can see, the graph here, this is the graph showing the change in the mass of catalyst in a chemical reaction. It stays the same always. The volume of oxygen produced when all the hydrogen peroxide is decomposed is larger than when there is no catalyst present. No, catalysts only speed up reactions, they don't magically create more product. So finally, water and oxygen are the only products of the reaction. It's a weird one to go for, but basically they just want you to understand that catalysts don't change the nature of the chemical reaction. They don't create new products, they don't create more products, and the only thing they do is speed up the rate at which these products will form. It's always good to go through a process of elimination because most of them just simply won't make sense or break the rule of the thing they're asking you to investigate. At the end of the experiment with the catalyst added, the mass of the catalyst remaining is found. The method used to find the mass of the catalyst remaining is filter the mixture of products and catalyst, determine the mass of the filter paper and solid catalyst, subtract the mass of the filter paper from the mass of the filter paper and solid catalyst. This method would not give the accurate mass of catalyst remaining. Which of the following needs to be done to give a more accurate mass? So questions like these are quite challenging because there's a lot of information which your brain has to process and work through and, in a sense, imagine. So let's just work through it one by one. Filter the mixture of product and catalyst. So you can imagine you've got the product and catalyst here, you've got that liquid and the catalyst in there, and by filtering it, you separate the liquid product from the catalyst. So now you've just got the catalyst in the filter paper. Determine the mass of the filter paper and the solid catalyst. So you'd remove the filter paper and the catalyst, take it out and weigh it. So now you've got the mass of these two things here. Subtract the mass of the filter paper from the mass of the filter paper and solid catalyst. So you find out the mass of just the filter paper and subtract it from the mass of the filter paper and the catalyst, and you'll have just the mass of catalyst. Now all this makes a lot of sense. So where are we going wrong, or how can it be improved? Well, let's read through the answers. Dry the filter paper and catalyst before finding their mass. Obviously, if you've had a liquid product on there, some of that will still be on the filter paper and also in the catalyst. So you would need to dry it off to make sure that there's no product or liquid left and you're just getting the mass of the solid catalyst. So already that makes sense. Scrape the catalyst off the filter paper and find the mass of the catalyst. No, find the mass of the filtrate and not the filter paper. That's irrelevant. That's not what we want. Repeat the experiment. Well, no, you just make the same mistake. This is the only one which makes sense. A given mass of catalyst is more effective if it has a large surface area. State how you could increase the surface area of some lumps of solid catalyst. Always, to increase the surface area of anything or any solid, you break it up into smaller pieces. If that doesn't make sense, if you think, well, those pieces are getting smaller, don't think of the individual pieces, but the surface area created when you add all the pieces together, or the surface of all the pieces together. For example, imagine this was a strip of magnesium, and you were to count the surface area, the surface here. I'm just going to use arbitrary units. So let's say this is 4, this is 4, this is 1, this is 1. Now if I chop this into 4 little squares, you'll see that if you added this up, 4 plus 4, 8, 9, 10, that's the surface area here, 10 units. Whereas here, into 4 pieces, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we've got a gain of 6 units of surface area. So that makes sense. You can relate to that. If you want to dissolve a tablet faster, you basically crush it up and it'll dissolve much faster in water, like vitamin C. The experiment is repeated 3 times, once using a more dilute solution of hydrogen peroxide, once using a lower temperature, and once using a larger flask. In each case, all other conditions are kept the same. Circle the words that show the change in the rate of decomposition in each case. So in other words, which of these factors will affect the rate of reaction and how will they affect it? More dilute solution. Well, basically what that means is it's less concentrated. So if you reduce the concentration, if there are less particles sort of roaming around and knocking into each other for the reaction to occur, the reaction will happen at a slower rate, because chemical reactions happen when there are successful collisions between the reacting molecules. If there are less reacting molecules, there are going to be less successful collisions, or they will occur less frequently, like less dodgem cars in a dodgem rink. So it's slower. The temperature used is lower. Well, if you remove the amount of energy, or if you reduce the energy in the particles contain or have, you will basically slow down the reaction because they'll move slower. So slower. They'll have less kinetic energy. The reaction is carried out in a larger flask. That will not affect it. The only things that affect a rate of reaction that you need to know are temperature, surface area, concentration, and the use of a catalyst, all of which came up in this question. Finally, complete the balanced equation for the reaction and fill in the 2 missing state symbols. So let's begin. State symbols are these things here. AQ means aqueous. This means it's a solution, something dissolved in water. We know that H2O is a liquid, so we can just write a little L there, always lowercase letters, and oxygen is a gas, so a G there. The solid would be an S. So that's the first part done. We get 1 mark for that. Now we need to balance the equation. So if we start off here, we'll see that on this side we have 2 hydrogens and 2 oxygens here. So 1, 2, 1, 2. Always write down the elements in the order they appear on both sides. Make sure it's the same order. So no matter whatever this dictates, so hydrogen came first and oxygen came first here, if it's in a different order here, still write it the same here so you can compare it across more easily. Whatever you find on this side, you'll find on this side, so you don't have to worry about that. Right, so let's begin balancing the equation. Here we have 2 lots of hydrogen, 2 lots of oxygen, 2 atoms of oxygen, 2. Here we have 2 water molecules, so we have 2 lots of H2, 2 times 2 is 4, and 2 lots of oxygen, which is O1. You don't write a 1 there. If it's got no number in front of it, it's just default at 1. So 2 times 1 oxygen is 2, but you must combine it with the 1 on this side. Always look across. If there's a plus there. So there's 2 oxygens here, 2 oxygens here, which make 4 here. So we can see it's definitely out of balance, but it should be an easy fix. So we need to up this side. We need to basically increase the hydrogens and the oxygens. So what's the easiest way to do that? Well, the default number is 1, so we just need to go up 1 at a time until we balance it. So the next smallest number will be 2, so let's try that. 2 there. So that would mean 2 lots of H2, which would be 4, so we can cross that out and put 4, and then 2 lots of O2, which would be 4. 2 times 2 is 4, and we can see by doing that it's balanced. This is probably one of the easiest chemical equations you'd have to balance, which and the 2 marks come from writing the 2 there and the state symbols there.